What if I told you that the map on your phone right now is, it's lying to you by hundreds of
Oh,
miles?
absolutely.
Yeah, and not because of like a software glitch or, a bad signal or anything like that, but because of a mathematical illusion that is so deeply ingrained in our brains, we all fall for it every single day.
It's true. I mean, we are incredibly conditioned by the screens in our pockets and, the paper maps we grew up with.
Right.
We expect the world to just be a neat, perfectly visible grid.
Hmm.
But the moment you zoom out and deal with the actual shape of the Earth, well, that grid just shatters.
It really does. And that is exactly our mission for today's deep dive. We are going straight into the heart of this spatial intuition trap.
Yes.
Based on a really fascinating stack of sources we have today, we've got geographic models, 3D sphere diagrams, and some incredibly striking boots-on-the-ground photography.
Really amazing photo.
Yeah. And we are going to track down the exact center of a massive triangle drawn across the globe. And in the process, we're going to see how our reliance on a flat map just completely and utterly tricks us.
It really is the ultimate trick.
Yeah.
Because when you take a three-dimensional curved planet and you flatten it onto a two-dimensional plane, like your phone screen, you are forced to make massive compromises.
Right.
Shapes have to stretch, distances have to warp, and, your common sense about where things actually are goes completely out the window.
Completely out the window. Okay, so let's unpack this and set the stage for everyone listening.
Okay.
Imagine a standard world map, just the kind you've seen a million times in a classroom. Oh, no. Picture a giant, bold red triangle drawn right across the middle of it.
Taking up a massive chunk of the northern hemisphere.
Exactly. But to really understand what we're dealing with, we have to define the three corners. The vertices of this giant triangle. Where are they actually anchored in the real world?
Let's start with point A. This is the ultimate starting line for our global coordinate system. It's the intersection of the equator and the prime meridian.
So that's 0 degrees north, 0 degrees east.
Exactly. If you were floating there, you'd be in the Atlantic Ocean, just off the western coast of Africa.
Right. The geographical 0, point.
Right. Now, to get to point B, we draw a line straight east. Picture a distinct red line in the sources, tracing right along the Earth's equator.
Hugging the curve of the planet.
Yes, for exactly 1/4 of its circumference. That puts point B at 0 degrees north and 90 degrees east longitude.
Okay, so where is that exactly?
You'd be bobbing in the Indian Ocean, directly south of the Bay of Bengal.
Got it. So we have the entire bottom base of our triangle sitting perfectly flat along the equator.
Correct. And then we have point C, which is the apex, the very top of our triangle.
Okay.
And that is the North Pole itself, exactly 90 degrees north.
Okay, so to translate this into a mental journey for you, because visualizing a static line on a spinning globe can be tricky. If you were to physically hike this out, here is what you'd do. You start out treading water off the coast of Africa at that 0 mark.
Right.
You travel a quarter of the way around the entire world to the east, right along the equator. Then you make a hard left and head straight north.
All the way up.
All the way up through Asia, across the icy Arctic Ocean, until you are standing directly on the North Pole.
Yeah.
And then from the pole, you head straight south, right down the prime meridian until you arrive back where you started. You've just traced this massive triangle.
And when you draw a shape like that on a sphere,
Yeah.
you haven't just drawn a standard triangle.
No.
No, you have created an equilateral spherical right triangle.
Okay, wait. An equilateral right triangle.
Yeah.
That sounds like a geometry oxymoron. Because, if it's equilateral, the angles are all 60 degrees.
Yeah.
If it's a right triangle, it has a 90-degree corner. It kind of can't be both, right?
On a flat piece of paper, you are absolutely right. The internal angles of a flat triangle always have to add up to 180 degrees.
Right.
But on a sphere, the rules of geometry fundamentally change. Think about drawing a triangle on a deflated balloon.
Okay.
When you blow that balloon up, the surface curves outward, and the lines you drew start to bow and stretch.
Oh, I see.
Because the Earth's surface curves away from itself, every single side of this triangle, from point A to B, B to C, and C back to A, is a 90-degree arc of a great circle.
So they're all the exact same length.
Yes. And remarkably, all three internal angles where those lines meet are exactly 90 degrees. It is a perfect 90-90-90 triangle.
Okay, my brain is already hurting a little bit. A triangle with three 90-degree corners That means the angles add up to 270 degrees.
Which is only possible because the canvas itself is bending. It's the magic of spherical geometry.
Man, okay, so we have this perfectly symmetrical, mathematically gorgeous red triangle sitting on the Earth.
Yeah.
But that's just the setup. The real mission here is finding the center of it.
Yeah.
Because if we look at the source diagrams, they draw a blue line from each of those three 90-degree corners, cutting inward across the land masses, and they intersect at a single point right in the middle.
The exact center.
Yeah. I want to find that point. So what does this all mean for finding the middle? Let's use some basic intuition here.
Okay, go for it.
If the bottom of the triangle is sitting at 0 degrees latitude, the equator, and the very top of the triangle is at 90 degrees latitude, the North Pole,
Right.
then the center point has to be exactly halfway between them, right? Halfway between 0 and 90 is 45. So the center of this triangle must be at exactly 45 degrees north latitude.
And you have just confidently walked right into the intuition trick.
Seriously. But it looks so obviously correct on a mat.
It looks correct because you are visualizing the Mercator projection.
Oh, right.
You're picturing a flat rectangle where the lines of latitude are stacked up like rungs on a ladder, perfectly evenly spaced.
Yeah, exactly.
But a sphere isn't a ladder. To find the true center, you basically have to throw the flat map in the trash. Okay. We have to map this out in three-dimensional space using an XYZ coordinate system. And the only way to do that is to start at the very center of the Earth's core.
The actual core.
Yes. That molten center is our origin point, our 0, 0, 0.
Okay, we are going deep into the Earth's core. I'm with you. Picture us standing in a hollow room right in the center of the planet.
Right. From that core, let's redefine our three corners, not as GPS coordinates, but as vectors.
Vectors, okay.
Think of them as three incredibly long steel poles jutting out from the center of the Earth, piercing the surface at our three corners.
Oh, that's a good visual.
If we set the radius of the Earth to 1, what mathematicians call a unit sphere,
Okay.
point A, off the coast of Africa at the prime meridian, extends purely outward on the x-axis. So its 3D coordinate is 1, 0, 0.
Makes sense. It's pushed all the way out to the crust on the x-axis, but hasn't moved an inch in the y or z direction.
Precisely. Now, point B, over in the Indian Ocean, is exactly 90 degrees away to the east. It shoots out from the core purely on the axis.
So its coordinate is 0, 1, 0.
Correct.
Okay, so x is Africa, y is the Indian Ocean.
And point C, the North Pole, points straight up from the core. That's the z-axis. Its coordinate is 0, 0, 1.
Wow. 1, 0, 0, 0, 1, 0, and 0, 0, 1. It's almost eerily clean.
It is.
Like when you strip away all the complicated geography, all the oceans, the continents, you are just left with this beautifully simple, pure mathematical structure.
It is perfectly symmetrical. So to find the middle, the geometric center of these 3 points, we just add those 3 vectors together.
Okay, well, I can do that math. 1 plus 0 is 1. We just get a 1 in the x, a 1 in the y, and a 1 in the z. So the dead center of our triangle is at the coordinate 1, 1, 1. Done. Let's pack it up.
Not quite.
Wait, really?
Think about where that 0.111 actually is. Remember, the surface of our Earth is exactly 1 unit away from the core.
Right.
If you go 1 unit forward, 1 unit right, and 1 unit up, you are now floating in outer space, way outside the sphere.
Oh.
The vector, our invisible steel pole, is pointing in the exact right direction, but it's way too long. We need the point on the surface of the Earth, not in orbit.
Ah. Because moving diagonally in 3D space pushes you further out than just moving along one axis.
Exactly. So we have to normalize it.
Normalize it.
Imagine that invisible pole sticking out from the core, passing through the crust, and ending out in space at 1, 1, 1. Normalizing it is like sliding a ring down that pole until it rests perfectly on the Earth's surface.
Okay, I like that. So how do we slide the ring down? Like, what's the math?
We divide by the vector's length. To find the length of that pole from the core to 1, 1, 1, we use the 3D version of the Pythagorean theorem.
Right.
We take the square root of 1 squared plus 1 squared plus 1 squared.
Which is the square root of 3.
Exactly. So to pull our coordinate back down to the Earth's crust, we divide each number by the square root of 3.
Oh, wow.
Our true center point is 1 divided by the square root of 3, 1 divided by the square root of 3, 1 divided by the square root of 3.
And if you run the decimal on that, that's roughly 0.577 for each of them.
Yes. 0.577, 0.577, 0.577. That is the exact mathematical center of our giant triangle in three-dimensional space.
Okay, that is satisfying to hear, but My phone's map app doesn't exactly speak in 3D sphere vectors.
No, it doesn't.
If I type that into a search bar, it's going to completely error out. We need to translate this back into the longitude and latitude we actually use to navigate the world.
Right, so let's tackle longitude first. Longitude is just the east-west position, which is determined by the relationship between the x and y coordinates.
Okay.
Since our x and y coordinates are exactly equal to each other, they are both 1 over the square root of 3, the longitude is perfectly split down the middle of our 90-degree slice.
Yes. Okay, half of 90 is 45, so the longitude is exactly 45 degrees east. I get a minor victory here.
You do?
My flat map intuition actually worked for the east-west direction.
It did. And that's because the east-west symmetry holds up along the equator. But what's fascinating here is how the latitude is calculated.
Oh.
This is where the flat map utterly fails you. In our 3D system, latitude isn't just a distance you drive on the surface. It's literally the angle measured from the Earth's core up to that point.
Okay.
And it is entirely determined by our z-coordinate. The mathematical rule is that the z-coordinate equals the sine of the latitude.
Okay, let me follow this. The sine of our latitude is equal to our z-coordinate, which we establish as 1 over the square root of 3.
Right. So to find the latitude, you take the inverse sine, the arcsine, of 1 over the square root of 3.
Hang on, I actually want to do this. Let me pull up the scientific calculator app on my phone.
Go for it.
All right. Arcsine of 0.5777. Wait, that does not equal 45 degrees.
Not even close, is it?
It's 35.264 degrees north.
Or, in traditional degrees, minutes and seconds, that's 35 degrees, 15 minutes, and 52 seconds north.
Wait, I need a metaphor for this because my brain is still screaming that halfway between 0 and 90 is 45.
It's hard to shake.
Why isn't the distance from the center up to the North Pole the same as the distance down to the equator?
It's all about the curvature.
Yeah.
And where the mass of the triangle is. Think of the triangle as a giant slice of pizza on a curved planet.
Okay, pizza. I can do pizza.
Down at the equator, the slice is incredibly wide. I mean, it spans a quarter of the globe. But as you go north, the slice gets narrower and narrower until it pinches into a single point at the North Pole.
So there is physically just like more planet in the bottom half of the triangle than in the top half.
Exactly. The vast majority of the surface area is clustered down near the bottom. That extra weight of the landmass and ocean pulls the geographic center of mass southward.
Oh, wow.
It drags it down from that intuitive 45-degree mark all the way down to 35.264 degree mark.
That is wild. Okay, so if the center's pulled south, how far is it from that center point to the 3 corners? If all 3 sides are equal and all 3 angles are equal, what's the actual distance from the middle out to the edge?
On a sphere, the shortest distance from our true center point to any of the 3 vertices, point A, B, or C, is an arc of precisely 54.7356 degrees.
54.7356 degrees. Okay, I didn't bring my graphing calculator to check that one, but I think I see where this is going. If I add our latitude of 35.2644 to that distance of 54.7356.
It equals exactly 90 degrees.
Wow.
It's perfect spatial symmetry. But it's a 3D symmetry where all 3 orthogonal axes, x, y, and z, contribute equally to the space.
Right.
It creates a reality that is entirely different from our flat map expectations. On a flat map, the center looks like it should be at 45 degrees. In reality, the true geometric center is pulled nearly 10 degrees further south because of the curvature of the Earth.
And just to put that in perspective for you, 1 degree of latitude is roughly 69 miles.
Yeah.
So our brains, relying on a standard 2D map, miscalculate the center of this massive triangle by almost 700 miles. That is not a rounding error. That is a completely different world.
It is a massive distortion.
But okay, the math and the 3D vectors are fascinating, but I don't want to leave this hanging in the abstract.
Sure.
I want to know where this point actually exists in the real world. Like if you were to parachute down to exactly 35.264 degrees north and 45 degrees east, where are your boots hitting the ground?
Well, if we take those precise coordinates and drop a red pin on a physical map, we land right in the Middle East.
And here's where it gets really interesting. What is actually at the exact center of this massive triangle?
That pure mathematical apex sits deep in the Zagros Mountains.
Okay.
Specifically, it drops right on the incredibly rugged mountainous border between the Kurdistan region of northeastern Iraq and western Iran.
Wow.
It is a complex, heavily topographical area. You aren't dropping a pin on a sterile white grid. You're dropping it on jagged rock. And I should note, While saying 35 degrees north, 45 degrees east is a convenient, rounded approximation that people might use in passing, if you are looking at a true map, you really need that precise 35.2644 decimal. Without it, you are standing miles away from the true center.
Right, because 35 flat would put us nearly 20 miles south of the actual mathematical sweet spot.
Exactly.
So we are in the Zagros Mountains, an ancient, formidable mountain range. But it's not just empty wilderness. What I love about diving into the research on this is that we can look at what it's actually like right near this mathematical anomaly.
The photos from the source material are great for this.
Yeah, let's explore the neighborhood around our dropped pin, because humanity has been living around this center point for millennia without ever knowing it was there.
The pin itself is in a mountainous border region, but there are two major human settlements relatively close by that perfectly illustrate the contrast of the region. Let's look west first.
Okay.
Just to the west of our center point, in Iraq, is the city of Sulaymaniyah.
Yeah, checking the geography here. Sulaymaniyah is located about 50 to 60 kilometers west-northwest of our exact pin.
It's a major cultural and educational hub for Iraqi Kurdistan. It's a bustling, highly significant metropolis in the region.
And if you actually look at the photo of Sulaymaniyah from the sources today, it's a striking scene that completely defies what you might expect.
Oh, for sure.
When you think of a mathematical center point in a rugged Middle Eastern mountain range, you might picture something desolate, dry or ancient.
Right.
But the reality is this beautiful, highly modern cityscape. Like, picture standing in a plaza with bright blue outdoor pools where fountains are shooting arcs of water up into the air.
It looks amazing.
It feels almost resort-like. And behind the water features, you have these neatly manicured bright green trees framing modern multi-story houses painted in warm earth tones. They've got this sharp, dark trim around the windows. And towering over all of this modern architecture is a dramatic, heavily clouded sky that looks like it's about to drop a massive thunderstorm over the mountains. It is incredibly vibrant and alive.
It perfectly captures the modern dynamic reality of the region today. But if we look in the other direction from our center point across the border into Iran, we find Kermanshah.
Right. Kermanshah is located at about 100 to 120 kilometers southeast of our center point.
And Kermanshah has a very different profile than Sulaymaniyah.
Yeah, it really does.
It is a major industrial city, but more importantly, it is a deeply historical city in western Iran. The layers of history there stretch back to antiquity.
And the visual contrast in the sources is just breathtaking. If Sulaymaniyah is modern blue fountains, Kermanshah looks like a scene pulled directly out of ancient history.
Definitely.
Imagine walking up to this vibrant, incredibly calm, deep green lake. The water is so still that it acts like a mirror, perfectly reflecting the tall, dense green trees that line the bank.
It's stunning.
But the real focal point is what sits directly behind that lake. The water laps right up against this massive, sheer, pale, rocky mountain face. And carved directly into the solid rock of the mountain itself are these massive, deep archways and large, intricate rock carvings.
Yeah.
It looks entirely timeless. It feels like people have been standing by the edge of that green lake, looking up at those towering rock carvings for thousands of years.
Because they have.
Yeah.
And that is what makes this so profound. You have this incredibly abstract, purely mathematical calculation, a point derived entirely from 3D vectors, spherical geometry, and the square root of 3.
Right.
And it doesn't land in an empty ocean or sterile desert. It lands you exactly between a modern educational hub with blue fountains on one side and an ancient historical city with millennials rock carvings on the other.
Which really ties this whole deep dive together for me. Like, why should you care about a perfectly symmetrical spherical triangle?
Right, why does it matter?
Because if you were just playing a geography trivia game or simply wondering what sits at the exact center of this massive quarter slice of the northern hemisphere, you might think it's just devoid of math. But it's not.
Yeah.
It's a vibrant, ancient, and culturally rich mountain range sitting between two distinct, bustling cities. It brings the cold, hard math of a sphere right into the warm, messy reality of the human world.
If we connect this to the bigger picture, we started with a theoretical construct, a perfectly symmetrical 90-90-90 triangle covering a quarter of the globe.
Right.
We had to break through a very persistent illusion taught to us by every flat map we've ever seen, that the center of that space would simply be halfway up the grid at 45 degrees.
The intuition trap.
Yes. And we used 3D vector math, specifically the value of 1 over the square root of 3, to slide that ring down the pole and find the true geographic center.
Which was so satisfying.
And that math didn't lead us astray. It pulled us nearly 700 miles south, directly into the Zagros Mountains, to a highly specific, very real point at 35.264 degrees north, 45 degrees east.
It is a phenomenal journey from a red line on a map to a green lake in Iran. And it leaves me with one final thought for you to mull over.
Okay.
We just saw how our basic 2D max completely distorted our ability to guess the center of a simple triangle by nearly 10 degrees of latitude. We were wrong by almost 700 miles just based on our visual intuition. So imagine how wildly distorted our understanding of global flight paths or international borders or the true massive scale of ocean currents must be when we only ever look at a flat map on our phones.
That's a lot to think about.
If the map lies this much about a simple triangle, what else is it lying to you about right now?